So the lecture for today is about functional programming and tail recursion. Let's discuss the two keywords val and def for declaring variables and functions, and two ways of passing function arguments called by value and called by name. So we use this keyword val to declare a variable with eager evaluation. So what eager evaluation means is that we evaluated the initial expression, for example, this one, or this code block, initial expression, right away at the time of declaring this variable. The second keyword is def, which is used to declare variable with lazy evaluation. What lazy evaluation means is that, so for example here, this initial expression is not evaluated when we actually declare this variable c. We will evaluate this expression later when this variable c is dereferenced inside another expression. We also use this keyword def to define function. So for example, this function double, we define this function double with the formal argument x of a type int and function body x plus x. So we use this keyword def to define functions as well. And to declare a formal argument with the call by value, you use this single colon. And to declare a variable with the call by name, we use this colon and double arrow. So this function double uses its argument in a call by value style, and this function double n declares the formal argument n with a call by name style. So here are several examples of using these keywords and two ways of passing function arguments. So in the first example, we declare this variable a with the keyword val with the eager evaluation. So we compute the initial expression right away. So 7 is printed. In this example, we declare this variable b with the keyword val. So it's eager evaluation. Therefore, we compute this initial expression right away. So we will see that the message computing 7 is printed on the screen, and variable b is initialized to the result 7. In this example, we declare this variable c with the keyword def, so it is a lazy evaluation. So what that means is that even though this code block has this print line function call, we do not actually print this computing 7 because it is lazy evaluation. Now we define this function double and then make a function call. So in this case, this function double uses its argument with call by value. This is a call by value. So in this function call, you have to actually pass some concrete value for this variable x. So what that means is that you have to evaluate this actual argument c. So now you go back to the declaration of variable c and then start evaluating this initial expression. So you see that this computing 7 is printed here, and then the result 7 is passed to the function double. So finally, 14 is computed. In the last example, you declare a function double n, but this time with call by name. Okay. So as I said before, the best way to interpret the call by name is textual replacement. So in this example, let's make a copy of this function body x plus x, and then replace every occurrence of this formal argument, the first one, the second one, by the actual argument. So now you have c plus c. So calling this function double n with argument c is equivalent to evaluating this expression, c plus c. Now, let's compute the first instance of this variable c. C is defined with lazy evaluation with the keyword def. So you have to evaluate the whole initial expression. So computing 7 is printed. And then you evaluate the second instance of a variable c. And then you have to go back again to the declaration of this variable c because it is lazy evaluation. And then you evaluate the whole code block, the whole initial expression. So computing 7 is printed again. And then finally, you obtain the result of 14. Another example of exploiting call by name, the particular way of passing function arguments is logging. So in practical programming, you often wanted to use logging to report the progress of your program, or to print the error messages or warning messages, or to print the debugging messages. So what you do is you set this logging level to, for example, error, or warn, or info, or debug. Normally you set it to info, in which case you print these error messages, warning messages, and info messages. And if you'd like to minimize the size of your logging file, you, for example, set it to error, in which case only error messages are printed. And if you'd like to debug your program and find out everything that occurs during the execution, then you set it to debug, in which case all messages are printed. So this is how logging works. And the problem is, depending on the logging level you set, the argument, which is a string usually, because the string is printed on, string is sent to the logging system, this string may not be used at all. So here's an example. So we call log.debug. So this is going to be debug messages. And it turns out that building a string like this one is quite expensive because the string concatenation is exponential in complexity. So building this argument is very expensive. But suppose that the logging level is set to info. In that case, we construct this very complicated string only to find that it is never used because the logging level is set to info and we'd like to print it as debug messages. So we never print it, and you just pay the price for constructing this complicated string. So this can be a problem in practice. So the response from Scala programming language is to exploit call by name. So in this example, we have this debug function with a formal argument message using call by name. So because it's call by name, we never evaluate this expression unless it is actually printed. So we have this is a debug enabled Boolean variable, and this Boolean variable is set to true only if the logging level is set to debug. Now suppose that the logging level is set to info. In that case, this is a debug enabled is set to false. So therefore, if this is false, you never evaluate this complicated expression. So you eliminate the cost of constructing this string. So this is the standard solution to the problem of avoiding the cost of building strings in logging in the case of Scala. In the case of Java, we have a different solution. Here's another example of exploiting call by name, a particular way of passing function arguments. We'd like to implement log, and the way that you use a log is you first acquire a log, and then you take some action, and then you release the log. And the problem here is you have to make sure that the lock is released eventually, no matter what happened to this action. So for example, even if this action raises an exception, like fails with out-of-memory error or fails with IO exception, you still have to make sure that the lock is released properly. So a common solution to this problem is to place this action inside the try construct and to place this release inside finally construct. And by exploiting call by name in Scala, you can have a very elegant implementation. So here are two functions that exploit the call by name. So the first function read has an argument eval, which uses a call by name. And then you first acquire the log, and then evaluate this expression, and finally release the log. In this way, no matter what happens to this argument eval, you eventually release the log. So here are examples of calling these functions. You can pass any code block as an argument. The point here is this code block is not evaluated at this point. It is evaluated when we actually evaluate the argument. So you can think of it as replacing this eval with this code block. And similarly, you replace this action argument with this code block. So in this way, by exploiting call by name, you can achieve a very elegant implementation of this common design pattern in Java. Let's review the syntax for defining recursive functions in Scala. So this example implements recursive function for greatest common divisor in Scala. You have two arguments and return type int, and here you make recursive call. In order to define a tail recursive function, you have to first import this package, and then you have to put an annotation just before the function declaration. Scala recognizes this annotation and makes optimization as necessary. So this is how you define recursive functions. In the programming assignment, you are asked to implement Pascal triangle with a recursive function. And it's pretty easy. It's straightforward to define the recursive function for Pascal triangle. It's just a matter of transcribe these recurrence equations into recursive function in Scala. So you'd like to use these recurrence equations in implementing the recursive function.